Hello, NewPick. This is Matt Taylor again, the open source community flag bearer for the Numinta platform for intelligent computing, and I'm coming back to you with another tutorial that I'm calling the One Hot Gem Prediction Tutorial. It's the first in what hopefully will turn into a series of tutorials. This is going to be the first and simplest one. And I am going to show you how this tutorial works. The source code is available online on our repository here at github.com/Numinta/NewPick, and it is in the examples, OPF, clients, HotGem prediction folder under one gem. So there's a README there, and we are going to basically build up this tutorial and sort of mostly from scratch so you can see how it works. So I am in my shell here. I've got a couple of files I'm going to start with, but aside from those, we're pretty much going to go from scratch. Let's look at the data first. So I've got a file here called rec_center hourly. It's a comma delimited file. And if you take a look at this data, it is basically just two fields or two columns. One is called timestamp, one is kW energy consumption for kilowatt energy consumed in that time or at that time. So these are already pre-aggregated hourly, most likely averaged over the hour. If we take a look at this data, let me just grab, I don't know, a few hundred rows and plot it. We are going to see some patterns emerge here, and which is great because that's what NewPick does well at, identifying temporal patterns. So as you can see, we've got a pretty regular pattern. So what this actually is date on the x-axis and kilowatts of energy consumed in a gym, a building, on the y-axis. And you can see daily patterns here. So every spike is a day. I'm going to back off on this a little. Let's take a few hundred less rows and see if we can get something that looks a little bit nicer. There we go. All right, now you can see it a little better. So we've got a day here and then a bump in between the days. So we've got a major pattern and a minor pattern here. That bump in between the days is actually when the cleaning crews came in the off hours of gym time and did their vacuuming and stuff like that. So they had energy consumed during that period. And there's also, you can sort of tell, there's some somewhat regular patterns during the day. There's usually an initial spike, and if you a spike in the first part of the morning. Sometimes there's sort of spikes at the end of the day. These probably coincide with people's work schedules as they're coming and working out. I'm not going to continue to dive in, but there's also weekly patterns. On the weekends, there's not necessarily as busy, it seems. The energy consumption is slightly different on the weekends versus the weekdays. So this is the data that we're going to be evaluating with within NewPick, and it's within this rec_center hourly file. As you can see here, we've got a timestamp and then an energy consumption value. So what we first need to do, because what we need is to create a NewPick model that represents the parameters for the CLA before we can start passing this specific data into that model. And the best way to get a model like this is to run a swarm over the model. So that's what we're going to do. There is a wiki documentation about what a swarm is on our wiki. I'm not going to go extensively into it, but I will talk about it as we go along. So I'm going to do this in Python. I'm going to try and do this in the simplest way I can. So I'm going to start with just an empty file here. We're going to call it swarm. I'm going to make it an executable Python file. And we will just do some of the obligatory stuff. I'm gonna do some cutting and pasting here to make it a little bit easier. So if it's main, we'll call a function on ourselves called swarm, and we want to tell it our input file, which is rec center hourly CSV. So assuming we're going to have a function called that, swarm input file. All right, we're not doing anything quite yet. Just get some formatting issues out of the way. Okay, so the first thing we want to do is we know there are these libraries, modules within NuPic that we're going to have to use. One of them is called the permutations runner. So here it is. From NuPic swarming, we're going to import something called the permutations runner. This is what has the function that will actually run the swarm. And it's called a permutations runner because what a swarm is a description of what the data looks like and where the data is, and then a description of all the permutations you want to run. And the swarm is a collection of permutations of those configurations, and it continuously creates models, passes data into them, and it kind of generates what the error score is, and then goes on to another one, and it's short for particle swarm optimization algorithm. And so it drops models that don't do as well, and it just continues to build new models and with different configurations based on the permutations you specify. So it will come back, depending on how large you make your swarm, with either a good set of model parameters, basically based on how many models it created and evaluated. It'll give you the best one that it found. So that's what we use swarming for, and it should give you a decent representation of your data to NuPic. The tricky thing is, to even run a swarm, to do anything, we have to have a swarm description. And I already have a swarm description here. Let's take a look at it. Swarm description. This is just a configuration. This isn't really code. It's just this is a Python dict. It could also be defined in a JSON file, but it includes some things that you have to tell it about the data. So, for example, included fields. This is defining the data. We know we're going to have a timestamp that is a date-time data type. We're also going to have another column of data in here called KW, energy consumption. I just showed you that in the CSV file. Its data type is float, and I've already identified the min and max value just by looking through that file. And this helps the swarm runner identify exactly what permutations it's going to run. Okay, so the stream def defines where the input data is coming from. In this case, it is we're calling it rec center, and the source is actually the file location. You have to have this file : / prefix on it. I believe that's the only supported protocol at the moment, so you must have this. And it's just pointing to the file in our current directory. So this could be absolute or relative file location. So really all this is all we really are worried about here is the name and the source file location. And we're just telling it to swarm over all columns. If we had lots of columns in here, we could restrict the number of columns we wanted to swarm over or include in our swarm permutations by name. Inference type is temporal multi-step because this is temporal data and it's a multi-step prediction. There's other options there like anomaly, temporal anomaly, just regular multi-step with no temporal aspect, and then non-temporal multi-step. But we know this is a temporal multi-step problem. Our inference args, this is where you can define how many steps ahead you want to make predictions. So we're doing a 1-step ahead prediction. If I wanted more, I could add a 5-step ahead prediction, a 10-step ahead prediction, etc. Now I would have 3 predictions for every input row, but we're just going to do 1 right now. And we have to tell it what is the predicted field. Well, I want to predict kilowatt energy consumption. Okay, the last 2 things, iteration count tells it whenever it creates a model, how many rows of data should it send to it before it ends its valuation. -1 means all the data, or you could just put 100 or 1,000 or whatever you like in there. And then we have swarm size, which is just small, medium, or large. Small is just for debugging, medium is usually what you want, and large will increase the number of models that are evaluated and take a very long time. So you only want to go from medium to large when you have a lot of time and you want to get as much, you want to get as good of a model out of it as possible. So this is my swarm description file. So back to our script that we're writing that's going to actually run the swarm. Let me just import that. So I can say, I think it was just called swarm description. So from swarm description, that's the file that we just showed, import, and I had it saved as a constant, swarm description. So that data structure is now imported within this constant called swarm description. All right, so now we're going to actually try and do the swarm. Okay, so in the end, what we need to do is call the permutations runner and call run with config. Now, if you watched my last tutorial, which was about predicting sine waves, I did this a little bit differently. Since then, I've updated the code to make this a little easier. So it's now run with config, so you don't have to write a JSON file. So I'm going to just kind of throw the parameters in here that are required for this. Let me clean this up a little, and then we'll fill them in. Okay, so I don't like the way so what we want is the swarm config as the first thing, which we know is actually swarm description. So this is the first thing. We're running with the config. We pass the config into it. And then we have some options, which we're going to tell it how many workers are going to be used for this. I'm going to give it 4. This means basically how many cores are going to be used and whether to overwrite any existing files that are created during the swarm. The swarm creates some temporary working files, and you have to tell it overwrite if you're going to do multiple swarms like in a row, just testing things out. So I always usually tell it overwrite. I don't really care if it overwrites the files. Okay, other than that, we need to give it an output label. Let's just call it rec center. We need an output directory. Now I am going to make a directory in here called swarm. So let me just stop what I'm doing there and do that first. And I'm going to call it a permanent work dir, perm work dir, or permanent work directory. Let's just call it swarm work dir. Let's do that. And we'll say absolute path swarm. So now I need to import OS because I just used it. So this is going to give me the path to a directory in my current working directory called swarm. And I don't know if it's going to be created or not, so we'll just say if not exists swarm work dir and make dir swarm work dir. And I'll do this the nice way. Okay, so we're creating a directory to run our swarm, for all of our swarm cruft to go into, and that's what that's for. So that's where we're going to call the outdir, swarm work dir. Okay. There's also the concept within the swarm of a permanent work directory, and we're going to set that the same because we're putting all of our output into the same place. And we'll just tell it verbosity equals 0, which I'm not sure even does anything, so let's just leave it out. I don't think it matters. Okay, so this is actually going to run the swarm. Let's see if that works. Nothing, why not try it out? Change mod 755 swarm.py swarm.py run. Syntax, invalid syntax. Okay. Let's look on line 6. Import, not input. And one more thing. I forgot a colon. It's going to be things like this. And otherwise, it is working. So this is what a swarm looks like. It dumps this stuff to the screen. And if you're paying attention to it, it's telling you details about the models that it's evaluating during the swarm process. I'm gonna, I think, kill this right now because this can take a really long time, even a medium swarm. I've got it running on 4 cores because I put max workers equals 4. If you want it running on more than that, you can increase that or decrease it however you like. I'm going to kill it. Unfortunately, these processes are going to live on, so I'm going to kill all Python processes. That will ensure that all of my swarm processes aren't running in the background. And what I'm going to do, because we're experimenting here, is I'm going to go into my swarm description. I'm going to give it an iteration count of 1, which, if you remember what I said recently, that will feed it 1 row of the input data per model, which will be very fast. And I'm going to tell it it's a swarm size of small, which means it's only going to evaluate 1 model. So by doing this, I can run swarm now, and we can watch it evaluate 1 model, send in 1 row of data into it, and return very quickly with the parameters for that 1 model that it tried, which is not going to be a very good model for our data. But at least we know that our swarm script did work. And now if you look into our directory here, you can see there is a swarm directory. This is where we are working directory for swarms. And it's got this model 0. This is where it dumps stuff for its swarms. And there's a model parameters file here. That's what we want. We want this model parameters file. So we could write some code to, dump that or move that from where it's at into somewhere that we want it, so that we can import it in our own script if we like. But we can also get it programmatically from the permutations runner because it returns this object when it runs run with config. But I know I'm going to want to put this in a directory here. So I'm going to make a directory called model params. And that model params object, let's take a quick look at it. We'll go into swarm model 0 model params. So it's a Python file, but all it is a configuration with one constant called model params. And this represents the best model it found during the swarm, although it didn't work very hard on that because we used a small swarm and it only evaluated 1. So this model params, I want to eventually go into this so that I can just import it. And I'm going to touch a file in here. This is a Pythonism called init, so that means that I can use that model params as a Python module. And I'm going to go into our swarm.py and let's do this. We know this function is going to return model params. That's the object that we want. And what I want to do is we'll say write to, we'll tell it model params. let's make this a little bit more explicit. Write model params. And we'll send it the model params object, and now we're going to create this function, write model params, okay. And so how we're going to do this is we need to be a little bit careful. I'm going to create this needs to be is going to be a Python file, but it needs the proper name. So unfortunately, rec center hourly or whatever is the name that we know. Let's just call it. Let's just say params. Let's get the out directory first. So we know the out directory is going to be. We're going to join our current directory. Get things cwd and the model params directory, right? So this is going to be our output directory. And we'll also do the if not path is dir. If it's not a directory, we're going to create it, make dir, so we don't have to mess with that. Okay, so the whole path of this file is going to be the join of, hold on, path, join, I forgot to put join here, there we go, of the out dir, and we're just going to call it, let's just call it model params.py for now, since we're just using this one. Okay. And now we need to open a file with open out path as a writable file as out file. Model params string. This is what we're going to pull out of that. We need to convert the model params object into a string. So how I'm going to do this is, so it's sort of easy. We could just say, I think we could probably just do this with JSON, but I want it to look decent. So I'm going to use this thing in Python called Pretty Printer. And I think it's just import pprint as pp. I'll just call it pp. I think that's pretty standard. No, we'll just call it pprint. Okay, import pprint. Okay, and model param string. We are going to create a little preprint object up here. Equals pprint pretty printer, and I'm going to tell it indent equals 2. So this will give us something that's readable, which I would like to have something that's readable. And then we can call, say, pp, that's our pretty printer, p format, which will turn whatever object we're about to pass into it, model params, into a string. So this will return us a string called model params string. Okay. And then we can say outFile.write. And we're going to tell model params equals, and we'll say, okay, we want a new line here. So we need to //n, and then this string we want is model params string. Okay, not so bad, right? And then we return the out path, which is the path to the model params file we just created. I doubt this is going to work right off the bat, but let's try it. See what we get here. So running the swarm, one model, one row of data, and it looked like it did actually work. Do we have a model params folder? And we have a model params file. So take a look at that. VI model params, there it is. It actually worked. Excellent. So this is the model params object we just wrote to file. That's what we need to create our NuPic model. Awesome. Okay, so that is essentially the swarm process there, sort of automated. Now that we've got that working, what I'm going to do is I'm going to go back into our swarm description. Let's see, I'm going to change this back into a -1, which means go over all the data, and a medium swarm. And I'm going to kick off a swarm. And I think I've got 4 workers, and that's fine with me. So I'm going to kick off a swarm, and then we're going to move on to another tab here. Bear with me, I will get one ready for you. Okay, guys, I am back here. So I've got one tab over here that's running a medium swarm over all of that input data. So that's going to take a while. So while that is running, we're going to go and move along and create another script which is going to actually run the swarm. So vi run.py. So this is going to be our runner. I'm going to also make this one executable. So, and then we'll add the if name equals main. We're going to have a function called run hot gym grand and def run hot gym. So some of you who know Python might be wondering why I'm not using the snake case, and it's because there's a NuPic convention within the Python codebase to use camel case for stuff, so I'm just trying to adhere to that. All right. So we're going to run this, and let's say we've got a model. Okay, so we're gonna make some assumptions here. So let's set up a few constants. Model params. How can we? Well, let's just think about what we need to do. We need to create a model. Let's break the steps down here. We need to create model. Okay. We need to run model, and during that run model, we'll deal with that then. So this is going to be a little bit different from the tutorial code and repository, but I'm trying to do this organically. So create model. We've got our model param, so let's import that. Import model params. And we've got from model params, import model params. So what we're basically saying is from the model params folder, import the module called model params, which is the file that we just wrote there. Probably could have named that a little better, but at least it's there. So we've got model params, and we need to actually create a model. So creating a model is pretty easy, but we need a model factory. And the model factory is part of the NuPic module from NuPic.frameworks OPF, which is Online Prediction Framework Model Factory. We're going to import a class called Model Factory. So the way we use this model factory is quite easy. Our model equals model factory create, and we use our model params. Get it? So model params here is the model params we just imported, which is coming from that file that we wrote in our step where we ran the swarm. Okay. We also need to enable inference on this model, which means tell it what our predicted field is. So there's a function, enable inference, and we're going to tell it predicted field is, what was it? Kilowatt energy consumption, right? All right, and return the model. Okay, so we can say we've got a model, created the model, run the model, and we need a function that runs the model. Def run model. So how do we run the model? Okay, so we're just going to kind of wing it here. Our input file is the same that we were using with the swarm, rect center hourly.csv, right? And so we are going to need to open this thing up. Actually, let's call this input file path. Our input file is open input file path. Readable. Okay, so that's our input file handle. And we're going to create a CSV reader, but before we can do that, we need to import it. CSV module package, from Python. CSV reader equals CSV reader input file. So now we've got a CSV reader wrapped around it. There are some header rows that we want to skip. Next. Too many. So there's 3 header rows in that data file that are not data, they're just headers. And so now we're at the top of the real data. Okay, so now that we are at the top of the real data, we're going to start looping through. What we're going to do is, I think we can just say for row in CSV reader. And that is our row. Let's do a little count here too. Row set counter equals 0, 2 zeros, 1 0. Okay. And we'll just say if counter, so like every 100 we'll print out something. Thread, so many lines. Okay. And we'll just do this. This equals 1. All right, so we've got our row. So we're going to, you know what our model, we've got our model, we've got our row, so now we just have to pull the timestamp out. And we're going to need to, so this is the first column, that's our timestamp, and our consumption is our last column, the only other column is that. Now the timestamp is coming out as a string, so I'm going to need to format it. So for that, I'm going to need to import datetime. And there's a formatter I can use, datetime, strp time. So I give it that, and I give it a date format, which I like to put as constants. And the date format is going to be the same if we look at our data. It was in the, it looked like this. All right, so Python, that's going to be lowercase m month and lowercase d day, lowercase y year, space, upper H, for M. Okay, so I think that's the date format that we want here. So that should be all right. So now we have our, now within our row, we've got our timestamp and we've got our energy consumption. Now we want to feed it into the NUPIC model. Okay, so we do that by calling the model and telling it to run and giving it an object. Object being, let's see, a dict timestamp, which is timestamp that we just created, and we called this kilowatt energy consumption, and we called it consumption in the variable name. Right, so we're passing one row of data into this model, and we run it timestamp and consumption. This actually returns us a result. This is the result that we're going to do something interesting with. Okay. Let's see. Now we can get the prediction out of this result by saying result dot inferences, and the key we're looking for is multi-step best predictions. Okay, so that's going. Remember in our definition, our sworn description, where we had prediction steps, and we just put 1, and I said you could put 5 or 10 or whatever in here. This is the predictions based on what you put there. So we said 1, so we want 1 out. If I had put 5, I could put 5 here and get 5 out, but I didn't. I only put 1. So this is going to be our prediction. So that's inside of our result objects, inferences dict. Okay, so that is our prediction. And let's see. Well, for now, let's just print prediction. I don't know. I'm anxious to see if this even works. So I just typed a lot of code, and I guarantee you it's not going to work. Change 555, run.py. Okay, no module, no model factory. Okay, probably I just need to, but that should be that. Is that right? Can't tell. Oh no, it's just not capitalized. There we go. Run. Okay, line 66, model config model. Okay, let's look at that. Oh, that's in model factory. But my line 16 and create model. So there's nothing, my model, so it looks like my model config is a little off. There we go. So when I created this model factory with the model params, oh yeah. So I know what the problem is. So let's look at the model params real quick. Model params. Oh look, there's a static, there's a constant variable here that I'm not using. I'm trying to pass in just the module itself, not the actual object within the module. So that makes total sense. So when we get here, this should say I'm creating model params not off the module, off of the model params object or configuration object within that module. Try it again. Hey, and it does seem to be working. So we're actually getting predictions. These are predictions coming out of NUPIC and being dumped onto the screen here. All right. So I don't want them to be dumped onto the screen. I'd rather see something interesting happen. So I've got this nifty little file here called NUPIC output. that I used as well in the sine tutorial. I'm not going to go over all the junk in here, but basically you can pass it values and predictions, and it will either write them to disk or plot them in Matplotlib. So that's what I'd like to try and do at this point, instead of just dumping them to the screen. So we're going to need to import that. Let's import it from NuPic output. Let's just import NuPic output. Import NuPic output. Okay. So in my run model, I'm going to create a model, or an output, equals NuPic output. Dot NuPic. Let's do file output first, and then we'll go with something different. Okay. So NuPic file output first, and I need to tell it the names of the things because it was written to handle many models at once. But we're just going to be passing it one, so I'm just going to send it a list of one thing, and we'll just call it rec center. Okay. So that's going to be reflected in how it writes the output file out. It'll be called rec center something. Okay, so we've got our output object here. And so we should be able to just use this instead of printing the prediction. Assumptions, predictions. So we've got our consumption, which is row 1 here. We've got our which is in the input row here. And we've got our prediction, which came out of NuPic. So in our output, we can tell it to write a row out after we've created it. This takes arrays of things, so you're going to see me wrap everything in arrays. So I'm going to send it the timestamp, because there's only one model, it's just one element in an array. I'm going to send it the consumption and the prediction. Okay, so now I have to be careful here. One thing I didn't do was close any of my outputs. So let me do that right now. I have an input file here that I never closed, so I should close that. After we've done the loop over everything, close. And the output also has a close function, which will close any output files. Let's see if that worked. Okay, let's run this. All right, it seems to be working. It's reading so many lines. Let's check on our swarm real quick. The swarm has finished, so I can have this available. And now you can see there's a rec center out file that's being written out. So that's what the NuPic output is doing. It's just writing it out to that rec center out file. So there it goes. It says it's done. Wrote all of the data to the rec center file. But I also want to make this plottable. So I don't know if I'm probably not going to do this in the tutorial, but I'll at least show you that instead of a file output, I also have a plot output available. So there's I just changed NuPic file output to NuPic plot output. Everything else stays the same. The only other thing that we need to do is shift the inferences. So what this does is basically it aligns the predictions with the input data so you can compare them like graphically. So this is helpful when you're charting. So there's something called an inference shifter in NuPic that does this automatically because it's so common for us to do it. So I'm going to go up and import this in the top here. It's called NuPic Data Inference Shifter, and the class is called Inference Shifter. And we'll use that as a tool right here. Let's see, you have to tell it, you send it the result and you get back a new result. So we tell it shift, actually I need to create the shifter somewhere. how do I create the shifter here? Let's do it outside of this loop. Let's do it right before the output. Shifter equals inference shifter. That's all. And then we just use that instance and tell it to shift results. Is that right? Is it just shift? Just shift. Shift and the result. So that will adjust that result so that the predictions are aligned with the actual values for plotting. So now when I run this, we'll actually get something dumped to our screen here. So we can see in the real time as NuPick is getting data and outputting predictions from this data file. You can kind of see in the background, it's read 200 lines now. We can see the performance of NuPick as it goes. One thing you will note here is the green line is the predicted line, and it's constantly trailing because it's only just seen these patterns. So generally when it's learning patterns, it's going to mimic the input as it goes along and just predict the last value that it saw until it gets a certain amount of data, and then it starts getting better and better at recognizing the patterns that are occurring over time. So we're just going to sit here and watch this for a while. Something seems odd here. Makes me wonder, it looks so, they both look so similar. Makes me wonder if I set this up properly. I'm going to pause this and reevaluate. I mean, those look exactly the same as far as I can tell, which doesn't seem right to me. Okay, guys, I figured out what I was doing wrong here. So I was just looking at that graph, and it looked exactly the same. The prediction and the consumption actual values looked so close, it just seemed very odd. It was just one was trailing, one time step behind. What I forgot to do was cast the consumption into a float. So it was getting not a float value for the kilowatt energy consumption. It must have been getting a string and then categorizing it somehow. So I don't understand exactly why that caused that problem, but I would assume it would have thrown an exception or something because it was getting a data type that it didn't expect. But it might have attempted to automatically box that into a float value, which could have turned it into who knows what. So now that that is fixed, you're going to see something much more dynamic here. So there you can see it's not just mimicking the input values anymore. It's actually kind of bumping up and down. It's getting to know the data a bit. Why don't I before we get into this, let me go into NuPick output and make this chart a little bit bigger. I happen to know exactly where that code is because I wrote it. Where did it go? I thought I did. There we go. Figure size. Let's make this a 20 and times 4. Yeah, it sort of worked. Oh, plot height. There we go. Let me just get a little bit bigger of a graphical display here. So I'm going to sit and let this run, and I'll come back when we get further down into the data so we can see how NuPick does picking up these patterns. So we're over 600 lines into it, and as you can see, these daily patterns it's getting a little bit better, a little bit worse at times. But so one thing you can notice is that it will occasionally nail the initial energy consumption of the day spot on. Sometimes it will trail behind a little bit, but like for example, this one that's just coming by, pretty much got that. It's got that one pretty well. It gets better. The more it sees this pattern, this daily pattern, the better it gets. And look how well it got this day. Very good accuracy there on the uptake and the downtake of energy consumption. It doesn't seem like it's quite gotten the weekends yet. This looked like a weekend just went by. So that's a longer term pattern. The daily patterns, it's seen a lot more of those patterns than it has the weekend patterns, just because it takes 7 days of data to get the week pattern down. But the daily patterns, it seems to be better. Just going to let it keep going. So we're only still, a quarter or a third of the way through the data at this point. Check it out now. It's really it's nailing not only the daily patterns pretty well, but even the patterns within the day. So the morning and afternoon bumps in energy consumption. It's also getting better at the weekends here. You can see that looked like a weekend. So we're now 2,300 lines into the data. We're about halfway through. And it's doing pretty well at this point. It's getting the cleaning crew coming in pretty consistently. Not bad. About 3/4 of the way through now, and Nupik is doing a pretty good job on these predictions at this point. It is very consistently predicting the daily patterns. Of course, it's you're not going to. It's not going to get every single thing, but as you can see, even patterns like this, it seems to do well predicting. Let's get the cleaning crews nailed down pretty good. And then the weekends, it's also doing well on. So at this point, it seems to have gotten a good understanding of the patterns within this data input. So that is pretty cool. I'm just going to let this run through. I appreciate all you guys watching this video. I hope it was informative. I'm probably going to try and continue this series. There's some other aspects of Nupik that I'd also like to write tutorials about, specifically anomaly detection. So adding some anomaly detection to this would be interesting. So you can see how confident Nupik is in the predictions that it's making. And then there's also some advanced swarming topics that you could take on when you have a bit more complicated data than we have in this example here. So looks like we are just about done with this data set, and there it is. So we've reached the end of the data. Here's the last 4 days of the data, which looks pretty good. Thanks again for watching. Take care, and hope you enjoyed this and it was informative for you.